Ready. Thank you, everyone. We are now in our third stop of the Gemini North Talk series, moving around the roads. We are today for the second day at TMT. I'm honored to introduce Roberto Decarli. I work with Roberto since now, well, we realize we know each other since 20 years. That's kind of painful, but also a pleasure. Roberto has his PhD in University of Insubria, working on the relation between black hole masses and host galaxies masses direct redshift. And then he moved to Heidelberg when he moved himself towards higher redshift, and he started to be part of big collaboration about the study of high redshift quasars. And in the meanwhile, a side project was one of the main participants to ALMA large problem to study the evolution of the gas content through the universe. And he did like a lot of other stuff. So there is like not enough time to explain everything that Roberto is doing. But after moving to Bologna, his major work is regarding the study of high redshift quasars specifically the host galaxies. And today, with not much surprise, we'll talk about the assembly of quasars and host galaxies in the early universe. So yours.
Thanks a lot, Emma, and thanks for hosting me. Well, it's a pleasure to be back after a year to give another talk at Gemini. Last year, it was the first time I was giving a talk. I think I was the first visitor of the series. So it was a big honor, and it's nice to continue this tradition. Last year, I made some promises of things you could expect from JWST, and I'm very happy that we can show some result today. So the topic today is assembly of quasars at high redshift. In particular, I will focus mostly on the host galaxies. But first of all, why should we care about quasars at this very high redshift? I think we can summarize basically in two main arguments. One is that the redshift 6, twiddle 6, the universe is about 1 giga-year old, and that doesn't give us a lot of time in order to explain the formation of the black holes, to assemble the galaxies around them, to form metals and dust in the galaxies, but also the large-scale structure where these galaxies are hosted, and also to ionize the universe. So studying high redshift quasars allow us to constrain a bit all these topics. At the same time, quasars at this very high redshift are extremely luminous, and it turns out they're also their galaxies are extremely star-forming. So we can witness conditions that are, first of all, they're ideal signposts for structure and at very high redshift. So we can search for the quasar that is relatively easy, and then search for the galaxies around the quasars where we know where to look. But also, they are very bright sources, so you can use them to study everything in between via absorption studies. And then, since these are extreme sources, you can use them to probe astrophysics of black hole and galaxy evolution in regimes typically not common in the local universe. So the question that my talk will be revolving around is how do quasars and the host galaxies form, with a specific emphasis on the galaxies. So if you, I don't want to upset the theoreticians in the room, but I think this is one of the probably few fields where observations are really leading the charge. This is because from a theoretical standpoint, if you want to address this problem in a cosmological context, you're facing really big challenges. First of all, the quasars are extreme, as we said, and because they are extreme, they are rare. There's typically 1 per cubic gigaparsec as a rule of thumb. So if you want to simulate a universe and study these kind of quasars in a cosmological context, you really need a really big volume, and then you need to compromise with the resolution. Also, you need to add the black hole starting point, so the seeds, somehow using some recipes, there's a big uncertainty on how to implement the black hole feedback and the feeding of the black hole as well. As a result, I think the status of the art from a theoretical point of view is nicely captured in this plot by Melanie Abuzi and collaborators, where they compare the predictions for quasars and redshift 6 from different sets of cosmological simulations. These are the color point in the bottom left part of this panel in this luminosity versus black hole mass plots. And they compare these are the prediction from simulations with the observed quasar population, which are the turquoise stars on the top right part of the panels. And you can immediately say bottom left, top right. So we're really talking about two different regimes in terms of luminosity and mass. And this is just a natural consequence of, in particular, the limitation on the volume. Cosmological simulations struggle to catch up with this kind of sizes, at least at the moment. What we can do better with simulation is to do zoom-in simulations, where you start with a massive source and you follow the evolution of the quasarous galaxies it's assembling at much higher resolution. And this has actually been a very exciting topic that would deserve a colloquium on its own by someone that is more qualified than me. But really the progress has been amazing. And now we can get image and snapshots of how the quasarous galaxy evolution should have happened, with a realistic prediction on the properties of the galaxies. Like in this case, I show the special distribution of gas, the molecular gas, and stars from a zoom-in simulation by Alessandro Lupi and collaborators. And you can see we can now start to talk about morphology, size, the distribution of the gas, starting to have some realistic predictions of the multi-phase distributions of the ISM, so density, temperature, abundances. And this allows us to study, for instance, the impact on the CGM, the role of the environment in the growth of the host galaxies. But also we can use these predictions to actually predict what observers should expect to see. And in this case, these are maps of the far infrared luminosity and the C+ emission. So observable quantities that we can immediately compare with the observations. And indeed, observation now are delivering a number of maps of, for instance, the dust emission and the gas emission traced by C+, down to a few hundred parsec scales, even at this very high redshift. These are a compilation of a few maps, including the one on the right appeared, I think, yesterday on the archive. And you see these are quasarous galaxies, redshift 6.6 to 6.9, all observed with ALMA. And you see on the left the continuum from the dust, the continuum emission from the dust. On the right, the gas as traced by C+. And then you can get velocity maps and dispersion velocity maps. And it's really exciting because already from these few maps, you can see that some host galaxies are more extended, some are more compact, like the central one. The central one seems to be nicely rotating disk, while, for instance, the one on the left is clearly showing a gradient, but also a non-rotating component. So it's clearly indication that it has at least some perturbed dynamics that probably has to do with the interaction with the companion source. I want to spend a few words on this one galaxy because it was one of the most compact sources we observed so far with ALMA, and where we pushed the resolution to the highest we reached so far. ALMA can do even better than that. But our selling point was that we could reach sizes of a few hundred parsecs, as we say, the resolutions of a few hundred parsecs. And this is an interesting scale because it's the size of the sphere of influence of the black hole. So the size, the volume where the black hole is expected to dominate the gravitational budget. So if you manage to resolve the gas dynamics there, you would have a direct measurement of the mass of the black hole. So that was our selling point, and indeed it would have been very exciting because, as you see from this plot on the left, where you have the radius of the sphere of influence versus the redshift of the sources, basically all the sources where we could measure the dynamical mass of the black hole in this way were at redshift 0.01 or so, right? So the very local universe, and this would be immediately a jump to almost redshift 7. So very exciting, but unfortunately we failed in the sense that the dynamic of the host galaxy as traced by the gas doesn't need any black hole. And the reason is that even in the central element, if you see this plot on the right, where we have the radius of the galaxy and the mass is computed in different ways, the dynamical mass budget, which is this purple line here, is basically completely dominated by the molecular gas. So there is a lot of molecular gas even in the central resolution element, and this molecular mass is basically higher than the black hole mass estimated from a broad line of the AGN. So even in the central resolution element, the gas, there is so much gas that is dominating the gravitational potential. So that was a bit unfortunate for their measurement, but still very exciting because it's showing that these galaxies are very compact. There is a huge concentration of gas and dust in the first 100 parsecs of the source. And this is really probably connected with the fact that the black hole is extremely luminous and the galaxy is forming stars like at crazy rates. Another thing that ALMA is doing and is delivering now is that we don't only have C++, that is the line I talked, yeah.
I'm just talking about the Roman results.
Yes.
Is it possible that there also you have the black hole of center from the galaxy?
So
or is this the Gaia position of the black hole?
In this case, it's very difficult because the host galaxy is small. It's really small. So it's possible, but I don't think there was indication of an offset. I need to double check. But being so compact, there's not so much freedom, unless it's really outside the galaxy, which would be strange. For the remaining result, yes. So Emma is alluding to the fact that in this host galaxy on the right, there seem to be in this case as well. They don't find a dynamical signature of the black hole, but the astrometry seems to suggest that the center of the host galaxy and the optical position of the quasar are slightly off. So the black hole might not be at the very center of the host galaxy. So moving on, I was saying the ALMA is also delivering not only C++, which is the brightest line, so the easiest access to study gas kinematics and high redshift, but also a lot of other different lines. This is a plot I'm putting together for a compilation with Tania Diaz Santos, and you see we have now more than 1,000 line detections at redshift larger than 1, and it's really exciting because 10 years ago we had I think we had 1 or 2 galaxies at redshift larger than 6, and at redshift larger than 1 we had like 30, 40. So now it's really exploding at an incredible pace. So and this is nice because you have different lines arising from different phases of the ISM. Some lines are from the ionized medium, some lines are from the neutral medium. Combination of these lines will give us information on gas properties, and now we can test, so we can do astrophysics of, thermodynamics of the gas, even at a very high redshift. The other new big ingredient I will talk about is, of course, the advent of JWST, because this opens a new set of opportunities for the study of high-redshift quasars. I'm showing here the results from a recent paper by Ding and collaborators, but there are many others in the literature that are appearing at a very high rate. In this case, they observed two quasars in this plot of luminosity versus redshift. They are not the most luminous quasars, redshift 6.4 that we know so far. And with JWST, you can do rays frame spectroscopy of the rays frame optical emission, and you get the classical optical spectrum of AGN, where you have the broad H alpha, H beta lines. From hydrogen, you have the oxygen lines, and the lines like the nitrogen lines, and so on. So the classical diagnostics that we typically use for local redshift studies, but now applied for quasar redshift 6 and beyond. And also we can probe the rays frame optical emission of those galaxies. And thanks to JWST's exquisite resolution and sensitivity, we can start to now detect some extended emission around the PSF of the quasar, which is basically the signature of the stellar population in those galaxies. So it's really exciting times for this kind of studies. So for the rest of the talk, I will talk about two main projects. One is focused on the multi-line observations of one quasar at redshift 6.5 using ALMA. So a few years ago, like 5 years ago, we did a survey of C+ in quasarous galaxy redshift larger than 6. We were very excited because it was the first time one could do more than just a few sources per paper, but we had like 25 sources. And we randomly picked the most representative source in the sample, which was obviously the brightest. It was this quasar PJ 183 plus 0.5, redshift 6.4. And what we did was basically to sample it with ALMA at different wavelengths. This gave us a nice coverage of the dust emission all the way up to the peak, as you see in this plot. And this follow-up observation also provided a high-resolution map of the dust emission. You can model this dust emission. You get the basic parameters like the temperature of the dust, which is in line with what we typically assume for these high redshift quasars, so around 50 Kelvin. We get a mass dust that is 10 to the 9, so it's very high mass content. If you typically assume that the gas to dust ratio is about 100, that means that this galaxy is 10 to the 11 solar masses in gas. Luminosity is pretty high, it's 10 to the 13 solar luminosities. And we also get basically using the information from the size, we get a constraint on the average optical depth at the frequency of C+, so around 1900 gigahertz rays frame, which is 0.4. So it's not negligible, the optical depth. The medium is very thick in this galaxy. But of course, we didn't choose the sampling of the dust emission randomly, but we choose it to sample a number of line diagnostics. In particular, we had M+, the 122 micron line, the oxygen 3 line, 88 micron, various molecular lines like CO, OH, and water transitions, and the C1 line. And the nice thing is that we can now have all these different traces for different phases, and we can test what kind of physical information we can get on the gas properties. So what we did was to take a number of templates. In this case, the left panel shows a black body with different temperatures. This is basically a proxy of what a star would do with different temperatures. And a single stellar population, again, in this case, we will change the age. And for comparison, the black line here is a template of an AGN. And basically, for each of these templates, you can integrate how many photons are energetic enough to ionize the hydrogen, ionize nitrogen, or oxygen 2, and so on, right? So you get the budget of the ionized phases from photoionization, and then you can compare that. You can compare these estimates for different templates and different different templates of the ionizing source. Right. In this case, Q is the, let's say, the rate of ionizing photons, and what you see in these plots is how many photons are able to photoionize oxygen twice versus nitrogen. And this will be something we can compare with the oxygen 3 abundances, nitrogen 2 abundances. At the same time, the neat thing of these fine structure lines, oxygen 3, nitrogen, C+, is that their physics is extremely simple. They're typically optically thin, and they're populated by collisions. And if they are populated by collisions, basically, you know that different levels are basically how many electrons are in different levels depends on the density of the gas and the temperature. So you can build diagnostics like this, where you have density of the gas and temperature on the two axes, and estimate just analytically how many electrons are in each level, right? So this is for oxygen 2 and nitrogen 1, which have the same electron structure because they have the same number of electrons, and you basically can populate. So you know how many electrons are here, you know how many electrons are there. You can calculate the rate of the de-excitation by radiation, and this will give you the line luminosity, prediction of the line luminosity. So you put everything together and you get basically a way to connect physical quantities like density of the gas or temperature with predicted luminosities of the lines and line ratios. Then you can compare with the observations. This is what we did in these plots shown as examples. On the left axis, on the left plot, you have the metallicity versus the hardness of the radiation field, which is in this case parameterized by the temperature of the black body. You can do it with the age of the stellar population. It's kind of similar. And what you see in this case is the ratio between the oxygen 3 88 micron line versus the nitrogen 2 102 micron. These are both lines arising from the purely ionized medium, but of course the ionization energy is different. So the higher is the ratio, you need harder photons, right? And this explains the big gradient on the x-axis. On the other end, there's a small dependency on the metallicity, and this is because oxygen is easier produced than nitrogen. So the ratio does change when you start to get secondary production of elements towards higher metallicity. Similarly, you can do prediction for other lines, like in this case, the nitrogen 122 versus 205 versus density, and you see basically the lines are my analytical predictions versus the points are prediction from cloudy radiative transfer, and you see that things match very well. And you can compare with the constraint from observation, which is this green shades, which point to densities of about 180. I think it's the 180. I think is the best fit, which is the value we use there. So relatively high density, but not extreme. So we're not talking about the diffuse medium. Most of the nitrogen line seems to appear to come from H2 regions. Another nice thing is that you know the luminosity of these lines. You can convert them with some relatively basic assumptions into masses. So how many elements you need to produce that luminosity. And this is what we get for the dense medium here on the left and the ionized medium on the right. And then if you believe you know your abundances, this is just by assumptions, but you basically can correct into how much gas is in the ionized form versus how much gas is in molecular form. So this plot is a bit busy, but you see basically that different predictions for the molecular gas phase suggest that we have a few times 10 to the 10, close to 10 to the 11 solar masses in the molecular phase, And then we have around 10 to the 10 solar masses in the ionized phase. So nice to see that the nitrogen and carbon based estimates are much higher than the one based on oxygen 3, which makes sense because probably not all of the oxygen in the galaxy is in the doubly ionized phase. So, you know, the bottom line here, and what I think is very exciting from all these stories, that we now can get, with relatively cheap ALMA observation, we can now get physical information on really key quantities like the gas density, temperature, and kinematics for galaxies that are redshift 6.5, 7 or so. So it's really fascinating. Moving on to the second project, we studied another system. It's a quasar satellite merger, redshift 6.2. This quasar was also part of our initial survey, and immediately from the original survey, we realized that the C+ emission, which you see in orange, was actually showing a very complex morphology. The quasarous galaxy is this sort of vertical bar from this higher resolution follow-up observation we did with ALMA. But then you really see there is an extended tail toward the west side and a very extended tail toward the east side. So this was clearly pointing to an interaction between the quasarous galaxy and at least one, possibly two companion sources. EMA then followed these sources up with VLT Muse and detected this enormous Lyman alpha extended emission around the quasar, completely only on the eastern side of the source. And our follow-up with HST revealed also some extended Resprem UV continuum emission, in particular in these two blobs here, which are basically consistent with where we expected the companion galaxies to be, showing that there are stars. So this is a Resprem UV broadband. This is basically the young stars in the companion sources. So we did the follow-up observation with GWST, and my postdoc Federica Loiacono has been working on the quasar phenomenology. This is the GWST spectrum of the quasar, and it's barely detected, as you can see. The signal to noise is around 300 per pixel. It's a level of signal to noise we were not used to for these high ratio quasars, to the point that we wasted so much time trying to fit all the single bumps in the spectrum, because you can't get away with poor fits when you have this kind of signal to noise. We did a fairly standard analysis in the sense, fitting the lines, the continuum, the lines, the iron template. I will talk about in a moment. Yeah, the broad emission lines, both the Balmer H alpha and H beta lines show a very nice Lorentz profile. You have some narrow component of the lines. The oxygen line shows the peak associated with the narrow emission line from those galaxies, but also a prominent blue shifted component suggesting that there's an outflow. In terms of the general phenomenology of type 1 quasars, if you're familiar with if you're not familiar with the eigenvector analysis, basically type 1 quasars show a range of properties in terms of how bright are some emission lines. In particular, the iron emission compared to the Balmer lines like H beta is usually summarized by this parameter R of the iron 2. And this seems to correlate with a number of properties like the width of the lines or the strength of the narrow lines. So I don't think we have a clear description yet at any redshift of what is the physical origin of this, but it's probably a combination of intrinsic properties of the quasar, Eddington ratio, orientation, different ingredients that play into this. But you see, basically, the purple points are the Sloan quasars, and the blue diamond is our quasar, and the other quasars observed in at high redshift are shown with with green and yellow symbols. And you see, basically, we are not discovering anything new. Our quasar falls in the middle of the generalized DSS population, so it's very standard type 1 quasar. We could test the black hole mass estimates using Balmer lines versus the previous maps that we got from the previous estimate we got from Eva's paper from using X-Shooter. And basically, you see that the black hole mass we get from Balmer lines versus the magnesium one are very consistent in our case. Again, our source is shown as diamonds, and also for most of the quasars, so nothing particularly special. The black hole masses are as good as we thought they were, so everything is good, and we can use this information to compare the black hole mass with the host galaxy mass. In this case, the host galaxy mass is derived from the AMA measurement. It's a dynamical mass, but keep in mind that the system is in interaction, so probably assuming that this is just a virialized source that is just rotating is probably not ideal. But we get the source is basically slightly above the local relation, in the middle of the points for many higher redshift quasars observed around with similar techniques. The interesting, the more exciting part maybe is that now we also have IFU data with JWST, and here I'm comparing the map that we get for H alpha in orange and red with the map that we got for C plus from ALMA. And you see that basically to first order, there's a one-to-one match, although it's not perfect. We have the quasar host galaxy. In this case, I already subtracted off the quasar emission, which is extremely luminous, so it dominates, and there's not so much I can recover in the center. But you have the quasar host galaxy around this vertical axis. You have the western companion and a sort of a bridge that is connecting the companion to the quasar host galaxy. There's the eastern companion, and then here there is some extraplanar gas, which is traced by oxygen and H alpha, but not in C plus. We'll come back to that later. We can get nice velocity maps. This is just a line of sight velocity of H alpha, and you see the prominent gradient in velocity. The western companion is blue shifted. The bridge is even more blue shifted than the companion. The quasar host galaxy has a velocity gradient. It's basically a rotating disk almost seen edge on, and it's moving this way. And then the eastern companion shows a velocity gradient. This was already seen in C+. It's really the textbook definition of a stripped satellite with a prominent tail and the velocity gradient getting away from the host galaxy. The quasar host galaxy, again, we have a dynamical mass that is order of 10 to the 11, although this game is better played with the C+ data because you don't have to go around the PSF of the quasar, and you're tracing an intrinsically dynamically cold phase of the gas, so it's better tracer of the dynamics of the system. You can extract spectra in all the region of this system, and you see here for the various apertures some of the key emission lines. In particular, the west companion has super bright emission lines. The oxygen 3 5007 angstrom line has a equivalent weight of like 1500 angstrom, so it's really luminous. But you can also see other lines like the auroral 4363 angstrom line. In some cases we get the helium 2 line, the sulfur in some parts. So it's really nice because then you can play a number of games like building the classical BPT diagrams. This is shown in these three plots, where we have the oxygen 3 over H beta as a function of different line ratios like NAM plus over H alpha, sulfur over H alpha, and oxygen 1 over H alpha. And you see, for instance, that the West companion is on the top left, and top means basically high ionization parameter, so harder adhesion field, and to the left means low metallicity to first order, because it's basically along this line, it's in the regime of photoionization from stars, from very young stars, not from the AGN, which would be this cloud on the right. The East companion has a bit less tight constraints, but again, similar properties. It's pointing to the left here in some parts of the system. It's a star-forming system, so we don't have a clear any sign that there is an AGN in any of these companion sources. The quasars galaxy, on the other hand, seems to have some sulfur emission that would suggest that even close to the quasars galaxy, the photoionization might be contaminated by the quasar. And this extraplanar gas is also photoionized by the quasar, so it's pretty high. I mean, the photo it's likely it's photoilluminated by the quasar, and it's not star formation. You can compare this with the grids of model, again with cloud in this case, and I will not go too much into details, but basically for the West companion we get a metallicity that's 0.6 solar and a pretty high ionization parameter, while for the Eastern companion we have we have possibly a lower metallicity and definitely a much lower ionization parameter. We can look at other diagnostics, in particular, here we have the H alpha over H beta, which is the Balmer decrement. It's a measurement of extinction. If you assume that the ratio is set by case-B recombination, you would expect this value here is 2.8, I think. So the fact that you observe higher values means that there is dust absorbing and reddening the emission. You can test the helium versus H beta. Helium requires hard ionization. So again, it's a good way to discriminate between AGN and star formation photoionization. And then you can use the oxygen 3 lines, the 5007 and the Aurora line, which is even higher energies, as a measurement of the electron temperature. And what we get for the Western companion is basically we have no extinction, basically consistent with no dust extinction at all. We have a fairly tight constraint on the helium emission, which may kind of rule out the AGN. You could still have an AGN in the case of low, low ionization parameter, but we saw from the oxygen line that is ruled out. So basically, the two information together basically strongly ruled out the presence of an AGN in the Western companion. And we get a measurement of the electron temperature. There's 16,000 Kelvin. Which is in line with you can observe in other sources also in the local universe. For the quasars galaxy, on the other hand, we start to see very high helium emission. We have some indication of obscuration, although the error bars are fairly big. We don't have constraints on the electron temperature, while constraints on the East companion are a bit loose here and not terribly informative. I'm almost done here. So the last thing you can check is we talked about the lines, but there is some continuum emission. The observation we did were achieved with a high resolution grating, which means we don't have a lot of signal per pixel in the continuum, but we can get an estimate of the underlying stellar continuum in the rest frame optical bands for the eastern and the western companion, and we can compare that with the photometry we get from HST in the rest frame UV. And what we get is basically, it's a very blue stellar population that is consistent with a very young age, 20, 30 megayear, which is probably not very different from the, the dynamical time of the interaction. So it might be that star formation, a younger generation of stars has been, the formation of this younger generation of stars was triggered by the interaction somehow. This plot on the right shows the star formation versus stellar mass plot, and the two galaxies, the eastern companion in orange and the western companion in blue, are shown where the star formation is computed in different ways using H-alpha or the continuum UV and infrared. And I find particularly interesting that, especially for the western companion, we have a much higher star formation rate estimated from H-alpha, which is a sort of instantaneous star formation rate compared to what we get from the UV continuum, because this is near UV, so you can get away with the older stellar population, more like in the 100 megayear time scale, right? So the comparison between the two, if correct, would suggest that really we are talking about very young stars. Finally, going back to the extraplanar emission, we talked about the Lyman alpha halo, and if you compare the maps of this extraplanar emission shown here in red and green for H-alpha and oxygen 3 respectively, with the emission from Lyman alpha, which is the bluer shade here, you clearly see that they're basically all pointing in the same direction. So it's very tempting to say we detect the origin of at least the central part of the halo, of the Lyman alpha halo, also in H-alpha and oxygen 3. We only really detect them at the center in the brightest part of the Lyman alpha nebula, which extend farther out. But we probably run out of sensitivity in this case, so we don't see much in the more extended part. This is interesting because, and Dema should correct me on this because he is the expert here, because the Lyman alpha to H-alpha ratio, luminosity ratio, should tell us something about the origin of the energy of the Lyman alpha emission. The idea is that if it's a recombination, you have a prediction on how much the ratio should be, and should be the case B recombination should be a factor 8.6, I think. So it's this horizontal line. So if you find something in that regime, it's a recombination. So you have photons that re-emit just through the cascade. If you have much lower values, then that's suggesting that there is dust in the CGM. So at CGM scales, you start to have reddening, and of course, you lose Lyman alpha first rather than H-alpha. On the other hand, if you have a very high value, that would suggest that it's not really recombination, but it's fluorescence or scattering of the Lyman alpha photons from the quasars that are just scattered around by the Lyman alpha. But because Lyman alpha is a resonant line and H-alpha is not, you only see Lyman alpha. So the fact that you get very high values is because you don't scatter much H-alpha as much as you do for Lyman alpha. And the value we find is somewhere pretty high. So a rough estimate, which still needs to be double checked, is in the regime of 100 or so, which in this case would really give us a conclusion on which kind of mechanism is powering the Lyman alpha emission. So I think I'm I can wrap up. We have conclusions for the first project. We measured very high dust content and opacity in this in one of these quasars. We got clear indication of copious amounts of gas, close to 10 to the 11 solar masses, both in the ionized molecular phase. And we started to get some information on the quasar phenomenology. In particular, one thing that I may not have spelled out today, but is that we find that the ratio between oxygen 3 and nitrogen 2, for instance, is consistent with the photoionization from stars. You don't really need a big contribution of the quasar, but of course, the quasar can also contribute. It's just not necessary. And for second project, we find that for the quasarous galaxy, it's a very matter-rich system, very massive, and the photoionization conditions are completely dominated by the quasarous contribution. The companions are half solar, 3 times 10 to the 9 in stellar mass, and star formation rates of tens, with a very young age of the burst. And for the halo, we seem to have indication of the that the origin of the powering mechanism is probably an outflow from the quasar, and then the Broadland region scattering really helps in the powering the luminosity of the Lyman alpha rather than recombination. And I will leave you with this one plot, which I think is the promise for the near future for these kind of studies, at least what I get really excited about for weird reasons, is that combining the capabilities of ALMA and JWST, we can now really get a whole plethora of you know, diagnostics that really can nail down, at least on a galactic scale, the physical properties of the gas, or you know, the mechanism in action powering the excitation of the sources. You can check if the gas, the dense gas, is dominated by the contribution of the AGN stars. You can get the densities and you know, ionization parameters. So you can get pressure, star formation at different ages. So we can really get a lot of physical information that will really be helpful, I think, for understanding how this system really evolved in the first mega years of the universe. That, I think, I take questions. Nice.
I had a question about the dynamical mass of the, I guess, the host galaxy in your second project. So you showed in the IFU data that there's a clear velocity gradient across the field of view there with the different companions. So how does the resolution of the ALMA data compare? And can you make a correction to the dynamical mass from the C2 based off of what you see here?
So I don't have the map here, but I can show you offline. The resolution of the ALMA data is 0.2, 0.3 arc seconds, so it's fairly comparable with the one we have for JWST observation. This is for the H alpha, we are towards 4.7 microns, so I think the resolution is around 0.2 arc second with JWST, so it's very comparable. The map can be much better traced in C++, and I can show you offline. I usually have this plot and I removed it for reasons, but it's much more homogeneous, and you can easily see the velocity gradient. The velocity is matched, so you see that we're talking about the same systematic movement of the gas, except for this component, which is not C++. Here it's interesting because on the southern side of the host galaxy, if you look with C++, it's not super obvious, but with ALMA, with the JWST, it's really clear. You have actually two dynamical components: the host galaxy, which is just the continuation of what you see in the gradient here, and then slightly off in terms of velocity, you have the bridge, which is further blue shifted than. And you really see double peaked lines here. it's nice when you have all this IFU data, because you can really move around and see, okay, this line is double peak because you follow here and one of the peaks disappear and the other pick up right. Let's say you know what they are seeing.
So you would claim the dynamical mass is probably pretty solid.
Yeah, the problem in that case, I think, is more the modeling per se, right? So the data are good. The C+ data you can easily, it's as good as it gets. The problem is that you have a rotating structure that is sort of edge on. You have some uncertainty in the inclination, but you have an uncertainty in how puffed up it is because of the interaction with the companion. And it might be that companion is actually disrupting or introducing a warp or something, and there is where you hide some uncertainty.
I was wondering, so before JWST, but even before ALMA, there were ways to estimate things about quasars, like their masses and other through more unsophisticated extrapolations or whatever. And so how well do the true calculations, now that you have the data, match up with previous more simplistic estimates?
So for the quasar mass, I think this is the answer. We were, especially for this IRA shift, we were using magnesium and other UV lines, which are worse calibrated, because most of the calibrations come from reverberation mapping campaigns in the local universe, right? So you have H alpha, H beta to tune, and then you use slow-on spectra of redshift 2 quasars to calibrate, to cross-calibrate, or redshift 1 to cross-calibrate. And this plot shows that we're not particularly off. I mean, we are within the scatter. We knew the black hole masses were not terribly off, because if we were making them, we were wrong in the sense that black holes were too small, were way small. So if instead of 10 to the 9, we would get a 10 to the 7 or so black hole, we would be in trouble, because these are extremely luminous sources. So you would have suddenly a quasar that, instead of being close to Eddington or around the Eddington limit, it will have 100 times Eddington, which it's not impossible, but it's not observed anywhere in the universe, right? So it would be weird. And for the other way around, if the black hole were way more massive than that, it was 10 to the 11, then we would be in deep troubles to explain how to follow them, because it's very early in cosmic time. So if that black hole is 10 to the 11, then I don't think we can easily explain it with any of the current models.
What about other values like the star formation rate? Or
for star formation rate, yeah. So star formation rates, so there are some uncertainties in the fact that I showed a nice case where you have a nice sampling of the dust emission, but in most of the cases we only have 1 or 2 points, so we need to assume temperatures and so on. And the uncertainty there is that typically what we say is that the total infrared luminosity, it's a tracer of star formation, but the AGN can also produce radiation that is absorbed by dust, and then it's radiating away in the infrared. So there is some uncertainty on how much the quasar is contributing with respect to the star formation to the total infrared luminosity. On the other hand, a lot of the probes we get for the molecular gas show conditions that are more suggestive of star formation excitation and so on. So it's possible that the quasar contributes to the dust heating at the center, at the very center, but not for most of the galaxy.
Is there any question from online while Olga asks?
So, do you have any hint on which is the largest scale structure around this object with the 2 companions?
Yeah, it's a very good question. So there was a study with SCUBA to search for some millimeter galaxies over a few, I think it was a few moving megaparsec scales. And indeed, we found a number of SMGs in the field of this quasar. They turn out to be, we did follow-up observation with ALMA, they turn out to be redshift 2. And we know it for sure because with ALMA, we very likely observed the CO726 and C1 lines. So you have 2 lines, so you're 100% sure about the redshift. And the thing is, when you select from SMGs, so from the dust emission, because of the negative K correction, the galaxy could be anywhere between redshift 1 and 8. And it's more likely it's redshift 2 or 3, right? Especially these dusty, massive galaxies. And there's a lot of universe between here and redshift 2, redshift 6. I don't think we performed an extensive studies at larger radii. We tried to do a mosaic and it was never approved. The Aspire program, I don't think, no, it doesn't include this, and it's basically kind of doing the same science. So now it's a bit difficult to argue with TAC that Aspire did this at redshift 6.5 to 6.7, and now we really want to do it for this one quasar redshift 6.2. It's a bit difficult to sell as a proposal.
Okay, but at the same, sorry.
Yeah, no, go ahead.
At the same time, you have a situation that can be related to lower redshift cases where, for instance, well, some of the observation that have been done, for instance, with the C3V survey, etc., there are very bright quasars that, well, locally, it seems that they reside in an average density. But then if you look on the larger scales, they are in an overdensity region. So it's like these galaxies have already sort of cannibalized their closest neighbor, because in any case, they reside in a very large overdensity. So I was wondering whether this could be just this step before with this bigger quasar that is sooner or later going to cannibalize the 2 other companions. And do you know whether simulations can also would support this?
Yes, so yes, and yes, I think is the answer. So the basically simulations agree that there is a variety and scattered, but for these very high redshift, high mass quasars, you need to have a rich environment. Maybe not the most overmassive halo, not necessarily the most overmassive halo, but you can only produce these massive black holes in big overdensities. And this is usually the trigger for our observing campaigns to search for structure around these quasars, like what Marco or Roberto are doing for 1030. It's very difficult. It has been very difficult so far because of observational limitations, sensitivity, the fact that you're observing in Lyman alpha within bad skylines and sensitivity field of view, these kind of things. And now with JWC, it's getting much, much easier because many of these observational limitations are bypassed, and you get with NIRCam, you can get slitless spectroscopy over a sizable field. And we are now getting for some of the, for the Aspire program, we have, I think so far we published only 1 quasar, and there's what, 20 candidates? 20 oxygen 3 emitters at the same ratios of the quasar. So you already know that in a relatively small field, you get all these galaxies. It's clear that they're overdensity. And by the time the program is completed, we will have a quantitative measurement of at least some sort of a, quasar galaxy cross correlation, which will give us an estimate of the halo mass and stuff like this. So we're getting there.
Any last second question?
I think if we have just a second, I'll follow up on that. So as Olga mentioned, and we see in C3VO, for example, that there can be local overdensities around these types of systems, but they're not necessarily embedded in the largest overdensity regions. So it's a matter of scale, right? So when you say 20 O3 emitters around this source, and you require a local overdensity to trigger a source like this, that still may not mean that they're sitting in the largest overdensities. It may be a local overdensity. So like in this case of the Aspire program, are you seeing things like on 500 kiloparsec scales? Are you seeing it on megaparsec? Like we normally see it at kind of 3 megaparsec or so scales.
No, I don't think, I need to double check. I don't think we get so far out because it's a single near-camp pointing. So I think it's 2 by 4 minutes or something like that. And but it's a single pointing per quasar field. So we didn't go to extremely large distances. But again, when you start, if you see a prominent structure, then you have fuel to argue we can ask for more time to expand. Right? That was the hope. It would be nice if it turns out it's several megaparsec scale. Then
with this argument, you are not far to having the selling point for a proposal. And
it seems like
all sky universities.
Yes,
yeah.
exactly. Why not?
On this note, why not? Thanks everyone, and thanks our speaker again.
So